My name is Dongyu Liang, advised by Dr. Singer. I want to talk about pore-resolving simulations to study the impact of char morphology on zone 2 combustion and effective factor models. Since coal and biomass remain widely used, the solid fuel resource understanding and their combustion and gasification is essential to optimize and design boiler and gasifier. CFD allowed us to study gasification procedure at a lower cost. In order to accurately represent the behavior, particle scale models are required in reactor scale CFD simulation. The particle morphology which limits the char particle conversion should be investigated. For this purpose, effective continuum assumption has been used to study char conversion at particle scale. However, this model cannot get accurate prediction once the voids are large. Some studies have attempted to model individual char particle with idealized structure, but none of this structure can represent the realistic char particle. The effective factor is a key particle scale factor used in reactor scale CFD code to describe the carbon conversion. Many idealized 1D effective factor models have been developed, but no research has evaluated their performance compared with the effective factor from the real char particle. To overcome deficiency of conventional particle scale simulation approach, a 3D pore-resolving model using real geometries obtained from MicroCity has been developed by our group. The complexity of the particle morphology that affects the char conversion is considered. In this study, 50 particles have been simulated. 5 1D effective factor models have been evaluated compared to the true effective factor from 3D CFD simulation. As shown here, all 1D models are based on the idealized geometry assumption. Here are the 6 representative particles we choose with their 3D morphology in the order of highly spherical on the left side to more complex voids on the right side. It is observed that the oxygen distribution highly depends on the structure of large voids. The accessible voids within the particle can enhance reactant transport, leading to higher oxygen concentration. The temperature distribution is nearly uniform regardless of particle morphology. In the following figures, the particles are arranged in increasing order of external void fraction. In this order, the most spherical particles are on the left side and the particle with network voids are on the right side. From the figures, the hollow sphere model and the flat plate model predict good approximations for only spherical-like particle, but more complex network-type particles require a new or modified effective factor approach. In this study, based on 3D pore-resolving model, we have found that particle morphology can significantly affect the reactant transportation. Furthermore, although reactor-scale CFD code often employ a distribution of particle size, they should also consider distribution of particle morphologies with a corresponding distribution of effective factor models to improve their predictive capability. As shown in the workflow, 1D effective factor model for particle with complex pore structure and automated image analysis routine using realistic 3D particle geometries will be investigated in the future.